Hello everybody and welcome. Today we're going to be taking a look at a project I made this weekend with a group of people at a hackathon, and we made an 8-bit computer in Minecraft. Now it is 8 bits, so all of the memory and the registers are 8 bits wide, and we have two general purpose registers that feed into an ALU which adds them together. And that's about everything that it can do basically. But we have 8 bytes of ROM here that we read the instructions and values from in memory. And basically the way it works is the way these registers are implemented is the registers sit directly in front of the ALU, and we have a purple line and a pink line, which will be the 2 bits that get fed into the addition operation at each step. So the purple line represents one coherent register, and the pink line represents one as well. And the way we write to it is this is a little D flip-flop circuit, and when this repeater closes, it allows the value to come in here and it gets locked in there. So we effectively have a value in memory that we can write to and read from. And the way that we write to it, the way we get the values to it, is along the bus here, which is this wide yellow thing, which has 8 bits on it. And let's say if we want to read a value from memory into one of the registers, we would open the read line from the memory, and that would transfer the value onto the bus, and then that value would make its way down one of these lines here, and we would come down here, and eventually it would be over here, and then we would write to it, and all of a sudden the value would be saved in there. And so basically, to do stuff on the computer, all you have to do is open the correct read line and open the correct write line. So you're taking a value from one place and moving into another place. And that's exactly what happens during each of the 6 instructions that we've implemented. So if we go down here to the instruction decoder, what this does is when the computer grabs a new instruction from memory, it will be loaded into this instruction register. And based on the value in here, it's going to light up a certain combination of the torches here, which is going to turn one of these torches on, like here. And then when one of these is on, we will give it a quick little pulse to one of the lines that comes off here. And each of these lines is just a path which turns the right read line on and turns the right write line on. And so, yeah, it becomes kind of a big mess of spaghetti when you have like 6 or more instructions, but actually the more you implement, it tends to actually get easier because you can reuse a lot of the lines. But yeah, it's got 6 instructions, so it can load values into the registers. It can add the 2 registers together. And we also have an instruction to output the display. And we have a jump instruction. The jump instruction has a hard-coded address value, but it would be pretty easy to implement a general purpose jump as well. But yeah, basically, we've written a program for it which calculates the Fibonacci sequence. So if I go ahead and turn the computer on here, pressing the on button, that will just turn this piston on, which is going to allow current to flow along this line, which is the clock. And so if I press this button, we'll give a quick little pulse to the clock. And now redstone will start making its way around the clock here. And you can see it, we have some lamps here to show where it's going. But yeah, basically the first instructions that it will run in this program is it will load the 2 initial values of the Fibonacci sequence into memory. And then it's just going to add the contents of the first register to the second and display that, then add the contents of the second register to the first and display that. And then we just do that in a loop by jumping back to the top. And so we should see the first value come up, which is going to be 1, pretty soon here, but it does take a while. There we go. So the computer is very slow. It takes about 12 seconds for one clock cycle to be executed. Your computer probably does about 3 billion clock cycles in 1 second, so it's a little bit slower. And we calculated the time it takes for this program to run. So in order for this program to finish execution and calculate all Fibonacci numbers under 255, it takes about 7 minutes. Now, we also wrote a C++ program for my computer, which calculates it, and that took about 0.017 milliseconds to run. So this program takes about 17 million times longer to run than the same program on the exact same computer. It's just not going through Minecraft to do it. But yeah, we should see 2 pop up here pretty soon. And yeah, but basically it's loading the values from memory, adding them, and displaying them. And if we can see over here the values that are being read from memory, you can tell by which sand blocks are above. And actually our value just changed to 2 there. This is 2 in binary. But we can see the flow of execution of the program by checking which sand blocks are up. So right now we are reading the 5th byte from memory, because this would be the 6th and 7th if we started at 0. Now we've moved on to the next instruction. And this will go down into our instruction decoder. And we can see the values in here, which is going to turn on the right instruction, like over here. And that's going to go and open the right lines to do what it has to do. And yeah, so what I'm gonna do is I'm gonna go ahead and speed this up. We just got our number 3 here. I'm gonna go ahead and just let this program run, speed it up, and you'll get to see all the values come through. And then we'll take a quick look at the assembly program that runs and just talk about some specifics there. But yeah. All right, now the program's done, and we can see that the display has reset, or actually, nope, there we go, we're getting the last value here. The execution of the program gets wonky at the end because we have a kill switch here, which happens when the last bit carries over, so when we get over 255, but you should have seen all the values of the Fibonacci sequence there over the course of the execution of the program. So yeah, now let's go ahead and take a look at the program we wrote. All right, so here we are, prepared the assembly program. So let's just go ahead and figure out what's actually on the screen. So in the first column here, we have the byte in memory that the instruction is stored at. And in this column here, we have the assembly code, which corresponds to what the instruction does. And here we have the opcode in decimal. And here we have the opcode in binary, so the number corresponding to the instruction. And let's just get right into it. So the computer starts reading instructions at address 0. So the first thing it will do is it will read the load pink 0 instruction. So this will store the value 0 in the pink register. And we can see at the bottom of our screen here, the pink register now has the value 0 in it. And then the next thing we'll do is we'll load 1 into the purple register. So here we go. Now the purple register has the value 1 in it. And the next instruction will display the sum of the 2 registers. So pink plus purple. So pink plus purple is 1, and we go to display the sum, and we see that we get 1 there. And then the next thing we're gonna do is we're gonna take purple and add that into pink. So 1 plus 0 is 1. So pink is gonna become 1. And we'll see that right here. And so pink becomes 1. And then we'll display the sum of the 2 registers again. So the sum of the 2 registers now is pink plus purple is 1 plus 1, and it's going to be 2. And we see our display now displays the value 2. And then what we'll do next is we will add the pink register into the purple register, and then purple register goes up to 2, because 1 plus 1 gets us 2. And then we get to the jump instruction. Now the jump instruction is going to change which address we're reading the next instruction from. So jump to 2 is going to take us back up here. So we're going to do this thing in a loop. So now what we will do is we'll display the sum again. Now pink plus purple is 3, so we get 3 on the display. And then we'll add purple to pink. 2 plus 1 is 3. Then pink becomes 3. Display the sum. Now the sum will be 2 plus 3 is equal to 5. And then we'll add pink to purple. We get 5. And then we'll jump back up to the top again. And we're going to display the sum. 3 plus 5 is 8. So our display turns to the value 8. And as you can see, we're getting all the Fibonacci numbers here. Now we'll add purple to pink. And now we'll display the sum of those, which is going to be 13. And yeah, and then we'll just keep doing this forever and ever. And that's how the program works. But yeah, each of these instructions is implemented in the game, and they are basically opening the right read line and the right write line in order to make things happen. So for example, the display sum instruction is opening the read line from the sum register, and at the same time it's opening the write line to the displays register. And so what happens there is then the display will update with whatever value is in the sum register. And that's basically the same for all of these. And then the jump register is the jump instruction is just changing the the register which holds the program counter, so which holds the current byte that we're executing. And yeah, so that's going to be it basically for the Minecraft computer. And hopefully hopefully it's cool. I think it's pretty cool. And hopefully you maybe learn something about computers and maybe even assembly code. So yeah, thanks for watching, and I'll see you in the next one.